Good morning, and welcome to Citedi, one of the 20 research centers of the Instituto Politécnico Nacional. Up to date, there are theoretical and technological challenges as alternative energy, nanotechnology, robotics, health, where control systems play an important role. Thus, it's a pleasure for us to welcome today research leaders in the field of the nonlinear systems who will bring some amazing experience addressing the current and future topics in automatic control in our first control workshop in Citedi. So, the objective of this workshop is to discuss open problems and recent applications involving control of mechanical systems, energy optimization, and problems related with disease as cancer. I would like to express my gratitude to the internal and external panelists, especially to those who travel long distance to come here supporting this event. To all participants via web and you. And finally, thanks to my work group. So please enjoy the sessions, the breaks, and the opportunities for discussing with our experts.
So let me introduce Professor. It's Professor Joseph Lesman. I'm going to say about some large principles. So Professor Joseph Lesman received an electrical engineering diploma from the Belarusian Technical Institute in Belarus. PhD degree in electrical engineering from the Illinois Institute of Technology in 1984. He spent a year as a lecturer and a postdoctoral research fellow in the Department of Electrical Engineering and Computer Science, University of Michigan and Harvard. At present, he is professor in the Department of Mechanical Science and Engineering, University of Illinois Urbana-Champaign. He is author of 60 journals and over 100 conference papers in several areas of control theory and practice. Dr. Berman is a recipient of the 1999 National Science Foundation President John Steer Award in Dynamic Systems and Control. He is Associate Editor of the National Journal of Dynamic Systems, Measurements and Control, and he is currently at the editor board of the Nonlinear Phenomena and Complex System. So, Professor,
thank you very much. I am not new to Mexico. My first trip here dates back to 20 years ago, and even before that, I met Professor Orlov through Professor Lukin, who was a research advisor of Professor Orlov in Moscow Control Institute. And it turned out that my own advisor, who moved to the United States about 1977, is Professor Mirko, who is now at the University of Michigan in Ann Arbor. So both of our advisors, Professor Orlov's advisor and mine, worked in the same institute, Moscow Institute of Control Sciences. And what I see now is basically the tradition of Moscow Institute of Control Sciences has been transplanted on Mexican soil very successfully. In particular, Luis's former student, Yuri Orlov, and my interaction with Yuri produced quite a bit of advances in adaptive control of systems governed by partial differential equations. And now there is a whole range of results that are coming out of researchers' efforts in Mexico. So there is quite a strong link between Russian Academy of Sciences, Moscow Institute of Technical Sciences, University of Illinois, where Yuri spent quite some time. Professor Lukin spent a lot of time with Professor Kakota, who's there at the University of Illinois. And now, Mexican Control Air Field benefits from this interaction. Basically, I would say that control, in part, is you may be in incident of control senses. So we're here carrying the torch of the place where much of the control theory was originated. The result that I'm going to present to you is very unusual. This is completely anti-intuitive, and one who says just came out of inspiration, and that inspiration came to my student, John Kim, when I confronted him with the difficult problem of controlling systems governed by partial differential equations. This work has a long history, and I will go through this several stages of formation of this area. We had a talk of Professor Kristich a couple of days ago, who is also carrier of the same tradition. He's a student of Professor Kvatovich, and who started looking at this area after Yuri and I developed quite already. So, the applications that we're looking into are numerous. Just two of them that I'm going to present here are the steel casting process and the future transport aircraft that is being developed by NASA right now. In steel casting process, which covers the continuous casting now, covers about 95% of the steel produced in the world. When I started working in this area, just getting fresh from postdoc at the University of Michigan, immediately Gary Steel, Indiana, which just is next door to Champaign-Urbana, about a 2 hours drive, posed the problem of how to control oscillations here in the mold, how to control the flow out of these nozzles, and how to control the stirring of the steel right here through electromagnetic stirrers. But the biggest problem here is how to control solidification. There are two problems with controlling solidification. One is that by the time the steel has to exit the containment zone, and that is where these two rolls stay, this is the end of the containment zone. So otherwise, the steel is contained in the zone. This is in blue, completely solidified steel inside the red part, which is called strand. It's a rectangular section. This whole thing is called strand. So this is fully solidified. This is not fully solidified. So what's going to happen here very often? That this red means that there is some liquid, some fluid, liquid steel inside there. So liquid steel all the way from here pushes on this. This is ferrostatic pressure. And as a result of that, this is going to bulge, and like a whale, is going to spout. And this is called wave. And that is about $1 million to fix. It's very dangerous. It can actually result in human loss of life. And that is the phenomenon that has to be contained. The other is that here in the bending and unbending areas, a lot of cracks appear. And those cracks are inside, on the interface between the solid and liquid inside the strand. And those are internal cracks. And also cracks outside, where this bending and unbending creates surface cracks. The problem with those is that when you have internal and surface cracks, they can combine and produce leaks right here. And the steel will start leaking out of here, and that's another big problem, this leaking steel. Even without that, the defect of cracks actually brings down the quality of steel, and it is not marketable anymore. So once this is out of here, this gets rolled, and then there is a storage facility with the whole beams of rolls of this still. When I started out with the project at Citedi, Indiana, by the way, Illinois and adjacent Indiana, where you have steel and now needle steel and many companies are located, Arcelor. This is like a Silicon Valley of steel. A lot of the firsts are there. For example, the first thin slab continuous casting process, where things are very thin. This is instead of 20 centimeters, this is just 10 or 8 centimeters. Everything is thinned out. The shell that is formed in the mold right here starts out very thin, and this is still the shell that is right here containing the steel is still quite thin. So everything is delicate, goes a lot faster, so the speed, the casting speed, this is the speed at which the whole strand moves, at which the product gets developed, produced. That is the casting speed. The casting speed increases, and human operators can no longer handle the process. At the workshop on Saturday, I explained in detail how to control this process through the boundaries. These are the sprays right here. The water sprays, these blue things. And there is the water going through the mold right here, through the mold walls. They are porous with a lot of channels in here, so where the water gets in. However, the current operation doesn't look at the boundary control. It looks at distributed control. The way it looks at this process is as if we are hitting a rod. So there is a rod, the internal disturbance, which is the temperature of the liquid steel, which stays at the constant temperature. The internal disturbance of this heat coming from the middle of the strand gets into the interface and affects the solid part of the strand, affects the solid shell from the inside. And from the outside, you have the heat sink, and this is taking the heat out through impinging of this water on the outer shell. So therefore, here is the shell. From the inside, there is a heat source from the molten steel. From the outside, there is a heat sink from the sprayed water, and the whole thing is like a rod. So if you think about it like we're cutting right here cross-section, then the whole thing becomes like a rod, and then we can think about two-dimensional. When we cut it like this, we will have two-dimensional cross-section of the strand. Inside there is liquid, outside there is solid. And then when we cut that one along the center line, we get one-dimensional rod, basically, which is like flexes. From the inside, this rod is heated up by the molten steel. From the outside, this rod is being cooled by the water. So what we have just done, we have done a model reduction from the three-dimensional through this cut to two-dimensional, and that was boundary control problem because of the sprays. And from two-dimensional boundary control, we just reduced it to one-dimensional distributed control, where the internal heat is distributed along the length of the rod, and the outer source sink is taking out the heat also in a distributed way by spraying the surface. Therefore, what I'm writing here is not boundary control from the boundaries as for the through process, but actually a distributed control, which is just an approximation of this 2D boundary control, actually three-dimensional boundary control, like a one-dimensional distributed control. Therefore, equation that I'm going to be considering is equation with heat equation with distributed control. So this gives rise to distributed control problem through this view of that cooling problem. Another point that will come up later in the talk is that the temperature inside the strand is more or less constant. This is the temperature of the steel, of the molten steel inside the strand. Therefore, the heat flux from the internal fluid can be viewed as constant disturbance. Constant disturbance. So there will be a rod with constant disturbance. And what can be better to reject constant disturbance than proportional integral control, which everybody studies at the undergraduate level. PI control rejects constant disturbance. What we're going to show that the way we will organize the system will produce distributed PI control. So we will reduce it to completely transparent control that everybody studies in the third year of their undergraduate program in control. These are the heat processes. They give rise to parabolic equations, where you have just heat dissipation and just parabolic electric operators on the right hand side that will give parabolic phenomenology in terms of eigenvalues all the way to the left half plane to infinity going, which is very important. So now you think of it that we are associating this process with expansion that also at the undergraduate level everybody knows. That's where Fourier series originated. When Fourier tried to solve heat equation, he did substitution in terms of separation of variables, and he got an infinite number of eigenvalues. And those eigenvalues were going all the way into left half plane, meaning that the motions associated with those were decaying extremely quickly as you go to the left half plane. We will see that quickness, that speed of decay in distributed parameters is actually producing extremely dangerous phenomenon when we wrap the loop around it. The next application is related to wave equation, or parabolic equation. Here is basically like a rod, but we don't heat anymore this rod. There is no heat exchange phenomenon anymore. There is flexing. So it's flexing, and that flexing is related now to wave equation, to wave motion. So now it's a flexible structure. So what NASA is developing is distributed actuation right here. So this is a rod. We can do it as a rod. And NASA is putting those flaps right here. This is shaped memory alloy. These are electric drive motors. So the whole thing is like flexing. The whole wing is flexing, and it can flex differently in different places like this. So this is where the flexing is on this rear end of the wing. And this has been built already. NASA is currently doing algorithms for this. I am in touch with the people who are doing this at NASA. And we probably will be trying to do joint project on that. But as far as the basic fundamental understanding of how to do it, they have been looking at this work that I'm going to present just from the point of view of understanding what can be done, which data structures can be used, what is the robustness of the setup, whether adaptation can be used. So these two applications then drive a lot of research as far as follows. And that gives rise to partial differential equation-based distributed parameter adaptive control. It could be model reference adaptive control, or it could be other forms of control, like L1 adaptive control that we recently done. So again, from Moscow Institute of Control Sciences came encouragement from Yakov Zolonovich Tsipkin, and Tsipkin was the advisor of Peter Kokotovich. So probably many of you know the name, he was some department. So Yakov Zamanich used to come to Urbana quite a bit in the late 80s, and I used to have a lot of talks with him, so he said that, yeah, that's an interesting area to look at. And also Jan Landau, who is very famous adaptive control idea, guy who started out with using Polos right here and applied it to adaptive control and gave rise to the whole the direction in adaptive control. So he also said that that's a nice area. There's a brilliant mathematician, Tom Seidman, who looked when I asked him what does he think about the area, and he said that he doesn't see why it shouldn't work. So it has to work. So then Mark Bayless did the first paper in adaptive control distributed parameter systems, and then Vic Sola, a colleague of mine, started working on this area, and then you rejoined it in the 90s. So, and the first result was compounds PhD thesis that gave rise to a lot of developments. It was published in Article Intersections of Automatic Control. So many of you know that this is a leading journal in the area, along with Automatica. In 1994, gave rise to a lot of work in this area. What about this adaptive control? Systems governed by partial differential equations. Well, adaptive control does work, so in this regard, Professor Citedi-IPN and Professor Landau were correct, and Tom Seidman certainly was correct. This is different from ordinary differential equation-based distributed adaptive control. Very, very different. There is clear difference and there is subtle difference. Clear difference is the persistence of excitation, when you need a lot of excitation to identify what I'm controlling, to identify the processes of the system, the properties of the system that you're controlling. Persistence of excitation now is also with respect to spatial variable, which is clear. This is from the right-hand side, from the input, but also from boundary conditions. So we have, therefore, spatially varying persistence of excitation concept. That's what we added to the picture in this paper. So fundamentally, we showed that the persistence of excitation, so much sought after in regular adaptive control, comes in a very different form in distributed parameter control, so spatially variable induced, spatial variable induced persistence of excitation. However, what came out is completely unexpected phenomenon. And this is that when you look at regular adaptive control for ordinary differential equations, there is like put in the average behavior. So if behavior is put on the average, even though it starts unstable and then gets stabilized on the average kind of, then it's okay. And this is not what happens in distributed parameter systems. There's no good on the average guarantee. Partial differential equation control is unforgiving. Because of imposedness, it's unrecoverable. Imposedness on arbitrarily short time interval leads to instant closed loop escape. No good on average guarantee. Why is that? You can understand this very simply in terms of Fourier expansion. So when we have heat equation, it is very stable, everything decays. But when we close the loop around the heat equation, then I will skip this. Well, actually, probably not good to skip this because you see here a lot of Yuri Orlov's contribution. That's when Yuri was already here. So this whole string of papers, reduced spatial autonomic reference adaptive control, and here is our big paper, algebraic intersections on automatic control through parameter systems identification with enforceable identifiability conditions. And those are the conditions that differ from finite dimensional ordinary differential equation case because those conditions are spatially induced, not just temporally, not time-able, but spatial richness here. And then you read it a lot with sliding of observed-based systems, with synthesis. We have here Leonard Friedman, who also does a lot of work with delay systems, which is a form of distributed system as well. So back to unrecoverability. This is our standard heat equation. The coefficients are here, specific heat and so on, are spatially distributed if we think of one-dimensional rod. So we will assume that all the coefficients are spatially there, but we can assume that they are constant too. So this x is not that important. You can think of it as a constant. So it's just the second spatial derivative, first temporal derivative. This is our input, distributed input that I was talking about. These are the flaps. Well, this is heat equation, so it will be heat sink. So we are taking heat out here. This is our control. So U here is the state of the system. This temperature, for example. For the heat process, U is temperature. Now F is our control input. So F is our control input, and it's not delta function, therefore it is distributed along X. It's a function of time. It's like we're spraying. We're changing the spray rate, but we spray along the long length of the rod. So for all this X, the X goes from 0 to 1, for example, if it's normalized, and it's a function of time. So this whole spray kind of goes along, and then it makes this U, which is the temperature, reach certain point, execute certain trajectory. According to this model, this new sub T, this is a model state. This is a model state, and this is the reference input. So reference sequence. So what we assume, if you look at this model, we will assume that this model is set by us, and this reference is given by us. And when we specify this reference, then this produces exactly the desirable trajectory for this system. Well, the only problem is that for this system, because it's computer code, we exactly know the initial conditions. And there is no uncertainty right here. Now, for this system, we don't know what are the initial conditions. Yes, especially if it's inside the steel, but we don't know what is the internal temperature. So it's kind of wobbly notion about the initial condition here. Well, coefficients also are not exactly very certain, so some robustness is of issue here. But nevertheless, this is the case for the heat equation, and this is the case for the wave equation, where we have now second derivative is it's like mass spring temper system, where we have x2 dots right here, but here we have second spatial derivative, and here first spatial derivative. So it's like flexible system, so it's like wave equation, but with some more terms right here, and forcing, and this is distributed like along the wings, and this is the reference input. So this is a reference model. So we are very happy with the behavior of the reference model, know its initial condition, we generate the reference input right here that drives this whole dynamics in exactly the way we want. So since we are very happy with what's going on here, because we designed that, what we want to induce is we want to force this system to behave exactly like this in hyperbolic case, or this system to behave exactly like this in parabolic case. And that means that we want the output oscillate error, which is the difference between the motion of this and the motion of that, or motion of this and the motion of this. This is the difference. We take the evolution, the behavior of the model, subtract the evolution, the behavior of the actual plant, form an error, And we want this error to go to 0 as time goes to infinity. And ideally, we want exponential decay, so that also the decay rate is getting into picture. We started out trying to mimic what's happening in finite dimensional adaptive control, model reference adaptive control, and we preserve the structure of the finite dimensional case. What is the structure? Here is our model with all these variables, and we know what they are because we compute them in real time. Here is our plot. Looks like a model, but coefficients A and B are unknown, and they are special variables. Unknown, that's the sense of adaptation. But the structure is there. And these equations are tunable parameters right here. So we will consider them in detail. So then, this forcing input, which is the heat sink that is taken out of the rod, this forcing input then is formed like this. Reference input that goes in here and forms the right behavior of these variables. Just reference input right here. Plus the other two variables. What do these other two variables do? They actually take care of the fact that these are not known. A and B are not known. So they tune, they adjust, they adapt. How do they adapt? Through adaptation law. The rate of change of these coefficients right here is proportional to these quantities. What are the quantities? There is some small epsilon that drives the adaptation rate. And here are two products, one product and the other product. Let's look extremely careful. Now, this symposium, this workshop is dedicated to some extent to nonlinear control. Nonlinear control. I will then point to everyone precisely that we have nonlinear system here and extremely bad nonlinear system. Why is so bad? Because this is the error. This is the error. And if you remember, the error is just the difference between the state of the model and the state of the plot. So there is this u already. This is the state of the plot. Whether it's parabolic or exopolic, that's immaterial. But what's important, that this error carries along the derivative with respect to x, with respect to spatial variable of this u. And that's another derivative of this u, which is the actual measurement of the plot. So you have not only derivative of the state of the plot, but you have derivative of the state of the plot times another derivative of the state of the plot. You have square. And that's probably one of the worst possible non-linearities. And probably from the undergraduate courses in ordinary differential equations, you remember that x dot equal to x squared or something like this gives rise to what? To finite escape time, right? Right? There we are. I will skip the math here, but there might come a time when we excite the equation and all our coefficients, and this is a closed loop dynamics when we put everything together. This is the original unknown parameter, this is the tuning coefficient for A, and this is the same for B. And then what happens that the system becomes closed, the closed loop, when this becomes negative. Why this can become negative? Well, you know, there's this very crazy reference input that we can put in like this. This F, this reference input right here, R. can be very aggressive, so the whole dynamics will not keep up with this, and at some point, that might change some. What happens? This is when everything is fine, and this is how we published paper in microequation sections. And everybody thought that that's great. But then Vic Sola said, oh guys, you have a big problem right here. This thing can turn out to be negative, and then all your eigenvalues of this heat equation, instead of nicely staying in the right-hand side, they will slew. Instead of staying in the left-hand side, they will slew to the right-hand side. And those very nice ones that gave you instant decay, those will come back to haunt you at the plus infinity, and then they will give you instant escape. And there is this instant escape, right here. So if we change reference sequence from this nice mild one, like this, reference input 5, no big deal, it's just constant, and this means we don't really do anything, we just execute a set point like a constant. Now we start moving a little bit, actually moving a lot. And if we start moving a lot, we immediately blow up immediately. Because that coefficient right here becomes negative at some point, and the system collapses. And it's very unlike ordinary differential equation world, which gives you some leeway. Okay, you can still recover. This is unrecoverable because you slew instantaneously eigenvalues to the right-hand side, and those that were far away at infinity in the left-hand side now are far infinity at the right-hand side. And they blow up instantaneously and the whole software crashes. And you can't recover. Ooh, that's so bad that everybody at the time said, ooh, this distributed parameter adaptive control is non-robust. It's just junk, basically. You just guys painted yourself into the corner. What is the problem? Well, you kind of reduce your saying to this childish case when you get the square. Sorry, you get like x dot equal to x squared, you know, and that's your adaptive control. So what do you want? It just doesn't work. And that's when we kind of got on for about 10 years until I got the brilliant student, Khan. And Khan was like for 4 years, staring at that, coming up with absolutely nothing. And at the 5th year, he came up with that. Where did he get this from? No idea. Just sheer brilliance. You know, when you stare at something for 4 years, and your advisor breathes you in the back and says, oh, it's time to graduate. And then the office of registrar says, you have to extend your visa, and you're running out of time. We'll have to ship you back to Korea, you know? So the guidance sits down and suggests this. Come on, what's that? He suggests a baby step. He says, okay, let's look at this F. And this F before consisted of, let's say for parabolic case, for the simplest case, it consisted only of 2 terms. What are these 2 terms? One is involving the state of the process unit. And the other is involving the derivative, second derivative of the state of the process. Well, and then when we form the error, you have this error multiplying that first derivative right here. And this multiplied first derivative of just the state. So he was thinking, how can we decouple? How can we liquidate this square right here? One square, u sub x from here, and the other u sub x from here, there is a square. How can we get rid of this square? Simple. How can we? What does it mean? Exactly. how to get rid of this square right here. And this brings along the setting that if we get rid of this square and have just first order thing, even with spatial derivatives, well, that's great, then this becomes linear, and maybe we can also eliminate this thing, this product, because there is also square, but square not in terms of u sub x squared, but in terms of u squared. Because in that e, there is u as a difference. So here is square, and here is square. This is square with respect to u, because this one is nu minus u, so there is nu times u minus u squared. And this is also square right here. So two squares. How to get rid of it? And what Kant did not realize, and realized later my other student Vivek, when we already chopped it up for multi-dimensional, for multi-agent systems that I'll show you later, that once we get rid of this square here and here, then everything that is in here, everything else is linear, and we have linearized that adaptation law. So the question is how to linearize the adaptation. Do you do geometric differential geometry, or you put some nonlinear function that unwinds it back? How do you do that? Well, you came up with two steps to do that. And this is actually related to what you may suggest a little bit earlier on in that paper, the first paper in the Journal of Adaptive Control of Signal and Signal Processing. So you will get this brilliant idea of let's kind of not let's not look at let's not look in this at this point at the state of the plant. Let's look at the state of the model, and let's form adaptive control where the control on the plant will be consisting of the same reference, and there is one error, that's fine, but everything else will be coming not from the plant output, but from the model output. Everything else comes from the model. So as a result, we get this adaptation law, where we have product, yes, but this thing has only v and u. And with respect to u, this is linear. And with respect to v, who cares? And this is because now v, because it's uncoupled, it's outside, it becomes perturbation. Just varying parameter. Could be q, could be any degree, because it doesn't matter. Because that u will be multiplied by external parameter, and this will be just a noise for it. It will be time varying, fine, but linear with respect to u. There's only one u. Now same thing here, only one u, and same thing here, only one u. So as a result, we get adaptation right here with respect to linear degree, first degree of u, linear. And not only that, this is the element that he introduced. There was nothing in the original law that had first spatial derivative. Equation does not have first spatial derivative. So here is a very interesting thing. Equation doesn't have first spatial derivative. So typically in finite dimensional case, the adaptive control law repeats the structure of the plant to some extent. The adaptation coefficients repeat the structure. Here he says, forget about the structure of the plant. We are not dealing with this. Now we want to linearize. And we will throw in something that the plant never had. And what the plant didn't have is first order derivative. Because wave equation has only second order derivative with respect to state, with respect to spatial variable. And heat equation has only second order derivative with respect to spatial variable. And he throws in first order derivative. Right here, completely anti-intuitive. This does the trick. If we now look at the closed loop, here are the equations. This is our model. It's completely external to anything. It's like external excitation. This is the plant. Doesn't have any first order derivatives with respect to x, only second order, and no derivatives with respect to s. And look at this control. It does have this error between this and this. That's the error. It does have the second spatial derivative, but of the model. And whoop, there is another one. It has now first spatial derivative with respect to the model. And it has this now with respect to the model. So now if you look at the adaptation law right here, this is like a nuisance with respect to you because this is just everything external, whatever happens right here, is not related to the loop. There is no loop closed around the model. Everybody sees that, right? Model is like external. No loop around the model. Everything is like outside. So the only loop is right here, and that loop does not involve any products or any squares. It just involves first order of the state of the plant. That's brilliant. And we are here in nonlinear symposium. So this is a weird kind of linearization of the area equation. I don't know how you come up with this. But it's there. And what does it produce? What do you think? Now we don't have x squared, we have like x dot equal to x. And that means, what is the domain of attraction if the equation is stable? It's global. So we got rid of the square, and immediately we attain global exponential stability of the whole thing. Well, that's not the whole deal, because global exponential stability brings with this extreme robustness. Before, and this is incomplete work because we are not even sure. We have not analyzed. Same thing for hyperbolic case. He just added right here. He just added right here for a spatial derivative in the hyperbolic case, and just extra terms right here. But the key is right here that this is for a spatial derivative, and this is coming from the model. So as far as adaptation laws, they are only containing linear parts with respect to closed loop. And that's the equation. Now everything is beautiful, just everything works, just beautifully. And not only that, we can put on one hand Dirichlet boundary condition, on the other side we can put Neumann boundary condition before the system didn't work. So that kind of robustness suddenly allowed not only to stabilize what we couldn't stabilize before, but something much bigger, which we don't yet know how to completely prove that. Let's see without the problem. It opened up the boundary conditions. We can have mixed, Robin, whatever, any boundary conditions. We don't yet understand yet why that global linearization, linearization is global, why the global stability is linearization suddenly opened up the realm of boundary conditions. Unclear. Just simulation shows we can handle any mix of boundary conditions. And this is, by the way, effect of adaptation. This is like P control without adaptation. And if we don't know the plant, for example, our coefficients change, but we don't know what is the change. If we just apply proportional control, well, there is no control. It cannot handle that. Now, if we apply adaptive control, that's what is error. Instead of this error, which never decays, that's what the error is now. So, this is mixed boundary condition. by the way. This is Neumann on one hand, very clear on the other hand, area is 0. The same now becomes very easily expressed through finite dimensionalization through wavelets, where we just decompose coefficients that we adapt in terms in the wavelet basis. It's very nicely, we just need 2 wavelets right here. So this is, for example, if we apply it to the discontinuous heating problem with distribution of temperature uneven, then without wavelets, simulation gives this convergence, with wavelets gives this convergence. We need only this allows the wavelets loop. We need only 2 wavelets right here. This is 1 wavelet. This is a lot better than the original one, no wavelets, which have very big deviation. This is still very crude. So we throw in another wavelet, and just second order expansion in terms of wavelets, just 2 terms, finite dimensionalizes the whole thing, so that we just have, for the adaptation error for the adaptation parameter, we just have 2 ordinary differential equations, and that's it. So I promise you that I will show you what happens for PI controlling distributed parameters. The same system as before, except we introduce disturbance observer. We add the disturbance now to the equation. Here is now disturbance right here. Now that is a disturbance, and that disturbance is now in the original system. That disturbance is now the distributed temperature, for example, from the internal heat of the molten still, of the liquid phase of the still that kind of goes inside the solid part and then propagates all the way to the outer shell, and we spray the outer shell. So now we can completely model through 1D the steel casting spray cooling process. So this is the heat equation, although there is some square there, but we'll just assume that this is just first order. This is our spray distributed, and this is our heat from the internal steel distributed. So that's the disturbance. We are now getting rid of this disturbance by introducing the model, which is the same kind of PDE, disturbance observer, and that system is becoming now more complicated, but no big deal. And here is how it works for the case of constant disturbance. Look at this. This is proportional control, and this is integral control. So this is PI controlling distributed parameter case, and adaptive at that, because this is embedded into adaptation. This all works beautifully. This is how it works. Tracking error without disturbance rejection under constant disturbance, and this is tracking error with disturbance rejection, with this adaptive observer, with this PI control. And let me finish my talk by saying that we started understanding what was going on, that we started understanding that we got global stability only after we broke this thing up into multi-agent form. And this is like taking a rod, chopping up, by the way, the estimate converges, taking a rod, and that's where I will finish, chopping it up into little pieces, and now you can imagine what happens. Now we have multi-agent set, which is like discretization of PDE. This, for example, what is that? This is just several first-order equations. This is like this. We're taking the rod, which is partial differential equation described. Here is the heat source. Here is the heat sink in the form of the sprays. And we are chopping it up into little pieces. And we are putting these pieces geometrically anywhere, but we are retaining the information between the boundaries. So we chop up the pieces here, but we retain the information about the boundary action through communication link. This is what this multi-agent system is. It completely retains hyperbolic behavior and parabolic behavior depending whether we take first order integrator right here or second order integrator. Second order, this is single integrator or double integrator. And this is essentially a discretized behavior of PDE, but now every one of these little things is an agent to itself, and they communicate only adjacently through boundary conditions, but here is giving passing the value of their own states to each other, and this whole thing then is expressed in the multi-agent form. These are the same adaptive control laws with this extra term that linearizes the whole dynamics. And it's only after we did this, and we started looking for the Plonov function and theorem, that my student who works after compounding discretization of that, this is how we stumbled on this. I was saying, what is a nonlinear Plonov function and theorem that you need? And he, after some 2 sleepless nights, comes with me with red lines. I cannot find any nonlinear Plonov function. It looks like Yoshizawa's theorem is applicable to this. What are you talking about, Yoshizawa's theorem? This is the theorem for linear time-varying system. He says, there's no nonlinearity. I don't see any nonlinearity. This is linear, but it's time-varying, you know, it's varying, so Yoshizawa's theorem. And then I said, wow, we were so stupid with my previous student that we didn't even understand what we did. And now we understand why it worked so well. Because we got global stability, because we linearized the system. So we didn't see what was behind the trees, right? We didn't see what was going on. So it's only after he took another 2 years to realize that transformation linearized the error equation and made global adaptive control law. So my message to you is that linearization comes in completely unexpected forms and shapes, and you have to meet it with an open eye, and at least not be so stupid that once you did it took 2 years to realize that, hey, there's a linearization there. Wow. So that's the message.